Science Help Now here. This is the algebra-based high school physics class. This is topic 6, work, energy, and power. In the first section, I'll be introducing the meaning of the word work in physics. In this video, we're going to look at 5 very simple problems in a largely qualitative manner, kind of get the quantitative aspect started so that you can see how to approach these problems. In the next video, we'll finish all of the math and actually calculate the work done in each example. In day-to-day language, the word work can mean many different things. For example, if a secretary is working, maybe she's taking notes or typing. If a doctor is working, maybe she's talking to a patient or examining the patient, trying to figure out what's wrong, trying to diagnose whatever problem the patient might have. If a construction worker is working, maybe he's doing carpentry. Maybe he's framing a house. He's putting up the wood before the other people come in and put up the sheetrock and all the electrical and the plumbing and stuff like that. If a pilot is working, he's flying a plane. If a clock is working, it's telling you the correct time. If the clock isn't working, maybe the clock is broken. If a car is working, it's able to be driven. If you're doing hard work, you might be exercising, you might be digging a hole, you might be babysitting. Right? There's lots of different nuances to the word work in day-to-day language. But in physics, the word work has a very specific meaning. Let's take a look at what work means in physics. In this video, we're going to look at some examples of very simple, everyday situations. And we're going to figure out how to decide, how do we analyze whether or not work is being done on an object by the physics definition of the word work. Now, here we have 5 techniques or things that you should consider to figure out whether or not work is being done on a particular object. So, I'm sure that you've been taking physics for a while now, and you've probably drawn a free body diagram. A free body diagram is an object or a group of objects. We'll stick with just one object, and on that object, you draw all of the forces that are acting on that object. You label the magnitude and the correct direction for each of the forces on that object. Now, if you're having trouble with your physics class, one of the things that you might not be doing, right, maybe you're not doing it, or maybe you're not doing it correctly, or you're not doing it consistently, is drawing diagrams, especially free body diagrams. All right, so one of the first things that we're going to do for each of the examples is draw a free body diagram. All the forces on the object, their magnitudes, and the correct directions. Number 2, in day-to-day life, people tend to talk about the person or the object or the machine that's doing the work. But in physics, you want to identify the force or the net force that may be doing the work. Number 3, keep in mind that in order for work to be done on an object, the object must move. There must be a displacement. If the object doesn't move, no work is done. So again, in order for work to be done, the object must move. Now, the other thing you should do is if the object moves, then write the magnitude and the direction of the displacement near, not on, but near your free body diagram. So you want to know all of the forces, especially the force that is doing the work, and you want to know the displacement when you try to figure out if work is being done on an object. 4. Keep in mind that the force and the displacement must be parallel. Now, I will be showing this to you in just a few minutes when we start the examples. But remember that force and displacement are both vectors, so they both have directions. And again, the force and the displacement must be parallel in order for the force to do work. If the force and the displacement are perpendicular to each other, no work is done. I will be showing this to you. Now, also, in a later video, I will do much more difficult problems where the force is at an angle and therefore only the component of the force that is parallel to the displacement is doing the work. We'll do those problems in a much later video. They're a little bit trickier. We'll stick to very simple examples in this first video on work. Now, finally, number 5, I just want to note here that the entire topic, work, energy, and power, are all scalars. Work is a scalar, energy is a scalar, and power is a scalar. Now, oddly enough, even though work is a scalar, work is defined as either positive or negative. It's just that in this case, it's not a direction. It's positive work or negative work, even though work is a scalar. Let's look at some of the simple examples, and let's use all 5 of these techniques or points to consider as we analyze whether or not work is being done on objects in the examples that follow. So in this first problem, what's happening is that we are lifting a 2-kilogram textbook half a meter straight up at a constant velocity. All right, so basically, here's the hand putting an applied force upwards on the book, all right, and causing the book to go upwards at a constant velocity. All right, one more time. Applied force from the hand, and the book goes up at a constant velocity. All right, so we want to draw a free body diagram. Now, again, if you're having any trouble with your physics class, one of the things you might not be doing is you might not be doing enough drawings. It's very important to do a free body diagram to thoroughly understand a problem. So here's a simple picture of the book. All right. Now, a free body diagram shows all of the forces on the object. Now, we could draw the hand. All right, I could put the hand here. All right, that's a terrible drawing of a hand. I could put the hand here, but it's completely unnecessary to have the hand there because what we're focused on is the book. All right, so let's not draw the hand at all. Okay? All right, now, we know that the mass of the book is 2.00 kilograms. But the first step, drawing a free body diagram, means you're drawing all of the forces on the object. Now, the force would be the weight of the book. So we need to convert the book's mass into weight. The symbol for weight is Fg, and the equation would be Fg equals m times g. The mass of the book is 2.00 kilograms. G, the acceleration due to gravity of the Earth, I'm not going to use 9.81. I like to use 10.0. Right? If your teacher wants you to use 9.81, then do that. All right, so here's 10.0 meters per second squared for the Earth. All right, so that means that the weight of the book, the gravitational force pulling down on the book is 20.0 newtons. Now we also know that we can make the gravity negative, in which case we're putting Fg is negative 20 newtons. All right, so from the center of the object, we draw the weight Fg straight down, all right, and we can label Fg equals negative 20 newtons. Now, the applied force up, we do happen to know the magnitude of the applied force up. How do we know it? Well, the book is moving at a constant velocity. That means, according to Newton's first law, remember, when an object is at rest or traveling at a constant velocity, the net force in that direction is 0. So that means that the applied force upward from the hand must be, Fa, must be positive 20 newtons. So the net force in the direction that the book is moving is 0. Now, we also know that the book is displaced half a meter straight up. So write down the displacement. All right, now don't put the displacement on the box, the book. Put the displacement, put the velocity, the displacement off to the side somewhere. All right, so here we have, all right, d equals 0.500, d equals half a meter. All right, and the direction is upwards. All right, so let's look at the little points that we made earlier. Draw a free body diagram. All right, identify which force is doing work. Well, it's either going to be the applied force or the gravitational force or both. We'll do that in just a minute. The object must move in order for work to be done. Well, we know that the object moved a half a meter, so we've got that. Now we want to look at the directions. All right, we want to see if the force is parallel to the displacement. If the force is parallel to the displacement, work is being done. Let's look at the applied force first. The applied force is straight up. The displacement is straight up. So what we have here, if the applied force, right, Fa is straight up, and the displacement is also straight up, right, work is being done by the applied force. Now because, okay, they're parallel to each other, therefore work is being done. And because they're both going in the same direction, this is positive work. Now remember, work is a scalar, but nonetheless, we identify the work as either positive or negative. All right, so this is positive work. All right, the applied force is doing positive work. Now, let's look at the gravitational force. Gravitational force straight down, displacement straight up. The gravitational force, all right, I'll put it over here so you can see Fg. I'm not doing anything here to scale. Nothing is to scale. All right, we just want to get the directions right. Now, the displacement is up. All right, now they are parallel to each other. So the gravitational force is also doing work, but because they are in opposite directions, the gravitational force is doing negative work. Now, so the applied force is doing work, the gravitational force is doing work, and as a matter of fact, these two works are canceling each other. All right, so the net work, all right, the net work is 0. The unit for work is the joule. All right. Now, what we're doing in this video is to start all 5 problems. Then in the next video, we'll begin each problem again and finish each problem with all of the math. We're going to calculate the amount of work, all right, and just finish the problems in the second video. So you're going to get to see each problem twice, which is much better for learning. You're not going to see it only once. You're going to get to see it done twice. All right, in this example, you are holding the 2-kilogram textbook up and you walk 3 meters to the right across the classroom. All right? So again, you're holding the book up. Your applied force is holding the book up, but the motion is to the right. Okay, so let's see what forces we have and whether or not they are doing work. All right, let's quickly reestablish everything. This example 2 builds upon example 1. All right, so here's the book. All right, we've got the mass is 2 kilograms. Now the shortcut to change mass to weight, multiply by 10. All right, so 2 kilograms becomes 20 newtons. All right, so the weight is negative, it's down, so we'll say negative 20 newtons. You are holding the book up, so vertically the object is at rest, meaning that the net force vertically must be 0, so the applied force upwards is positive 20 newtons, similar to before. All right, but what's happening this time is that the book is moving to the right. The displacement D is 3 meters to the right. Okay, so we want to decide if either of these forces are doing work on the book. All right, so the applied force is straight up. The displacement is to the right. All right, so we find that these two forces are perpendicular. So no part of this force, no component of this force, all right, is parallel to the displacement. So the applied force does no work. Applied force, right, moving to the right, holding the book up and walking to the right, the applied force does no work. Let's look at the gravitational force. The gravitational force is down, Fg. The displacement is to the right. All right, so again, they are perpendicular to each other. So the gravitational force, or the weight, the gravitational force also does no work. Remember, the force and displacement must be parallel in order for work to be done. The gravitational force does no work. Which begs the question, well, which force is causing the book to move to the right? Well, just very, very quickly, all right, if my hand were to move to the right, all right, my hand goes to the right, and there's no friction, then the book stays where it is, my hand slides to the right. But since there is friction between my hand and the book, right, as the book tries to stay in place, in other words, the book is actually trying to go that way relative to the hand, all right? So as the hand is going this way, the book tries to stay in place, but the friction, right, opposes that motion, and the friction, the direction of the friction is to the right, right, the same as the displacement. All right, so it is the friction between my hand and the book. Now I will draw the friction, all right, right there. Okay, FF. All right, and we don't know how much the friction is. Doesn't matter. All right, but the friction is to the right, FF. The displacement is to the right. All right, the force and the displacement, this force and the displacement are parallel. All right, so the friction force does positive work on the book. Same direction, positive work. All right, let's look at the next problem. Again, we're not doing everything, we're just introducing each problem. In example number 3, we're allowing the textbook, the same textbook from examples 1 and 2, to drop straight down 1/2 meter from rest. So, since we're allowing the book to fall, the hand is removed, there is no longer an applied force on the book. So the only force on the book is its weight. I hope you remember that this is called free fall. An object is in free fall when the only force on the object is its weight. So we allow the book to fall 1/2 meter. Now because it's falling down, we'll say that the displacement is negative 0.500 meters. We know that the weight, Fg, the gravitational force, all right, see, gravitational force, GF, Fg, whatever, all right, is negative 20. All right, and since the force that is doing the work is parallel to the displacement, the gravitational force does positive work on the book, all right, because they're parallel, and the reason it's positive work is because they're both going in the same direction. In example 4, you are pushing on a brick wall as hard as you can for 10 minutes. Your applied force is 15 newtons. Your hand gets very, very tired, but the wall doesn't move. Let's decide whether or not work is being done. So we draw a free body diagram. All right, you've got your brick wall here. Okay, now I'm going to draw the hand. We can erase the hand, but at least just to get started, I'm going to draw the hand. It's going to be a terrible drawing, all right, because I am not an artist. But we'll try for a fingernail on the guy's thumb, and here's the guy's fingers. All right, he's pushing on the wall. All right, and there's the hand. All right, it's not the worst drawing I've ever seen, but it's pretty bad. All right, so you are pushing that way on the wall. Okay, now for the free body diagram, let's eliminate everything except for the object that we're trying to move. All right, so the hand is pushing on the wall, all right, this way. All right, force applied. All right, now we also have a normal force back in this direction. All right, you've got the weight of the wall, you've got some friction, but let's just focus on the applied force, all right, and the resulting normal force. All right, now, what's important here is that the wall does not move. So therefore, your displacement is 0. All right, the displacement is 0 meters. The wall does not move. So it doesn't matter that you get tired. All right, you are not doing any work, even though if you were to push on a wall for 10 minutes or half an hour or whatever, you're going to get tired. But the physics definition, since the wall does not move, is saying you did no work. All right, no work is done because the object does not move. No work is done because the object does not move. In this final problem, we have a 3-kilogram copper box, and we're pushing it 2 meters to the right with an applied force of 10.8 newtons on a horizontal steel surface and at a constant velocity. All right, so here's your box. All right, here's your surface. All right, obviously the box is touching the surface, but you really don't need that surface to be there. In the free body diagram, we often want to focus on just one object. All right, so we know the surface is there. All right, now, let's draw all of the forces on the box. Now, we know that the box's mass is 3 kilograms, but mass, or kilograms, is not a force. We need to convert the box's mass to its weight. Weight is a force. So weight, Fg, is going to be m times g. The mass is 3 kilograms. G, I'm going to use 10 meters per second squared for the Earth. All right, so the weight of this box is 30 newtons. And we know that if you put negative 10, then you would get negative 30 because the weight goes down. All right, so let's put the weight of the box straight down. Fg equals negative 30 newtons. All right, now, the box is on a surface, right? So you have a normal force that is the same magnitude as the weight. All right, the box is on a flat horizontal surface. Therefore, the normal force is positive 30 newtons. All right, now, the applied force, 10.8 newtons to the right. All right, so let's put that here. All right, F applied is 10.8 newtons to the right. Now I'm just going to erase this. Copy that, pause and copy that if you need to, because I'm going to erase this, all right, because it's in the way. Okay. I didn't plan it perfectly. All right, now, since the box is traveling at a constant velocity, the net force in that direction must be 0. That tells you that the friction is going to be negative 10.8 newtons. FF equals negative 10.8 newtons. All right, so again, because the box is traveling at a constant velocity in this plane, all right, in this dimension, the net force in this dimension must be 0. So if they're telling us that the applied force is 10.8, we therefore know, because the box is traveling at a constant velocity, we know that the friction must be negative 10.8 newtons. Now, which forces are doing work? All right, the displacement is to the right. So label the displacement. All right, remember, displacement, velocity, acceleration, don't put them on the box. All right, just put them close to the box. Displacement is positive 2 meters, or 2 meters to the right. Okay, now let's see. All right, the normal force is up. The displacement is to the right. All right, that's perpendicular, so no work is being done by the normal force. The gravitational force is down. The displacement is to the right, so no work is being done by the gravitational force. Now, the applied force is to the right. All right, F applied. The displacement is to the right. All right, so the force and the displacement are parallel, so work is being done. Same direction, that's going to be positive work. So the applied force in this case is doing positive work. How about the friction? All right, the friction is to the left. All right, FF. The displacement is to the right. All right, they are parallel to each other, so work is being done, but because the directions are opposite, this is negative work that's being done. The friction is doing negative work. Now, because the applied force and the friction have the same magnitude, and obviously the displacement is the same magnitude, what we find is that this work, the work done by the applied force and the work done by the friction force, are canceling each other out. Therefore, the net work is 0. Right? No net work is done. The applied force did positive work. The friction force did negative work. When you add those two together, no net work was done. All right, so this was an introduction to looking at a problem, getting it started, deciding what force may or may not be doing work. So just remember, you want to draw a free body diagram, put all of the forces on the object. All right, then you want to see if the object moves. If the object moves, then write down also what the displacement is, the magnitude and direction of the displacement. All right, then you want to decide which force or forces are doing work. The way you make that decision, the force and displacement must be parallel. If they're both going in the same direction, the force is doing positive work. If the direction of the force and the displacement are opposite, then that force is doing negative work. Now remember, you want to see the next video where we finish each of these 5 problems. I think we did enough in this video. Let's move on.